I guess we can do a little sound check here. Why don't you reply in the chat if you hear me or not? Actually, I think the chat's a little bit behind schedule, so I think it's working. Looks like it's working from here. All right. Well, thanks for the confirmation. We'll start here in just a minute. Actually, we're gonna let people join us here in a few minutes. So I'll just chat here about some stuff. All right, let's get started. Um, Welcome back to Tech Talk with Grandpa. This is number 2, and tonight we're going to talk about my early days in computing. And we will wait for a few more people to come in because we have 3 viewers, and we'll see if we can get that to change here a little bit. Also, I don't know if you got the message or not, but it doesn't matter. We're going for it. So, we'll wait a couple more minutes. Well, I think I'll just kind of summarize what my last Tech Talk was about. It's really quite interesting to do these Tech Talks because I'm sitting in a dark room. Not dark, I mean dark room. I'm sitting in a quiet room and I'm looking at multiple screens trying to navigate all the stuff. And that was a little bit, well, it's kind of disturbing actually. But I guess you get used to it if you live stream a lot. And I got some feedback back from people that said they liked it. They liked the detailedness of it. And then there are other ones that said that it was a little too detailed and they fell asleep. So that's, that's par for the course. I think it's okay. I'm just going to keep going and we'll monitor the comments and we'll see where this actually evolves into. So I guess we'll go ahead and get started. So like I said before, welcome back to Tech Talk with Grandpa number 2. And we're going to talk about the early days of computing, and we're going to end up running a current production board, an embedded board, and get microPython running on that. So I'll just start out by saying that, let me see, in 1976, I have down here, we'll go over to this screen here. Not that one. We need to go to, where is my mouse? This one. Okay, so my grandfather had a HP 35, and he lived in Kansas, and he was a surveyor. And when we'd go to Kansas, we would see this on his desk. And as kids, we were not allowed to play with it because back in 1976 is when he had this, and its retail cost was $395.76. That's equivalent to $2,300 today. So this was quite an asset for him to have at his work, and this is he was a surveyor in Kansas, so this was one of the first scientific calculators that HP had come out with, and so when I was able to learn how to use it, I couldn't figure it out because HP calculators at that time were RPN, which is reverse Polish notation. So you'll see here that there's no enter key on there. I mean, there's no equals key, so you had to do your operations like if you wanted to add 2 plus 3, you type in 2, enter 3 plus. And so you kind of get a mindset of the way that math is structured, and it works out that if you do it this way, you don't need parentheses when you're doing your math calculations. All right, so that was in 76. And in 1977, when in the summer of 1977, this was the summer before I was in 9th grade, and we had heard that there was a computer, this mysterious thing called a computer down at the high school. And so we, rode our bikes down there and kind of ventured in and found the computer room, which was, they had allocated a classroom out of C Wing there in Los Alamos High School. And they'd taken that classroom and they split it in two. And half of the computer room now was machine room, which is where all the computers were. And the other half was where the operators, not the operators, the users would sit. So they had a PDP-11, and I kind of estimate it was called a PDP-11/50. And this is the picture of it here, and you could see this behind the glass in the computer room, the machine room itself. And you'd walk by the machine room, and then the classroom part of it was back in the back. And that summer of 77, the way you would interact with this computer is use these things called a deck writer. This is one of the original digital equipment deck writers, and this is it's basically like a typewriter. So you'd load up this paper, and you get this paper in a box, and this was tractor feed, so there was holes along the side of the paper on both sides, and you'd feed it into these tractor teeth that would kind of pull the paper out of the box, and so you could you'd load it up, and then you would log in, and we got login accounts. Let me turn off this timer here. I just saw that. So you would log in, and we had some guest accounts, and we would play around with this. And this is a traditional, dot matrix printer that made a lot of noise, and it was really slow. To print an entire line would be zzz, zzz, that type of thing. So at that time, they only had these in there, and they had about 12 of these deck writers. And these are really loud when they're operating, and they're actually pretty hot. So you'd sit in there, and you could type in commands and play stuff. But we didn't know how to program. All we knew how to play was Star Trek. So I looked around, and I found the source code for the original version of Star Trek that was available on these PDP-11s. And it was written about 1971, and you could actually run it on the PDP-11. So I'm going to go ahead and get that running for us here. So the first thing I'm going to do, I'll just tell you that I'm running everything in Docker again, like I did last week. So this is the command I'm going to run, and I'm not going to make an image. I'm just going to run a version of Ubuntu. So what I'm going to do is I'm going to build it first. And then I am going to do an apt update. So that's going to go out and get the repositories out. And then I'm going to do a dist update, which is actually going to update all the software that's currently on this container. And there's not very much. And then over on my desktop here, I'm going to copy the source code over into my container. So if we look in here, I just copied this as a zip file over. This contains the SST, which is a Super Star Trek source code. And in order to compile that, we need to, if we want to try to unzip that right now, the unzip isn't there. So we need to install that. We also need to do a kind of a combo package called Build Essential, which includes the make utility, the compiler, and all that stuff. So I'm going to go ahead and do that now. All right, so this is what it's going to download. So it's going to bring down everything that we need to build Super Star Trek, as well as unzip it. So as soon as this is done, we'll unzip it. We're almost finished here. Okay, so we're going to unzip that file, and you'll see here that we have a make file. So we're just going to hit make. And I guarantee you I have not played this, well, I don't know how many years is that? 43, 44 years. So we're gonna play Super Star Trek. All right, here we go. So it's a text-based game. Remember that we're using a deck writer, which is a line printer, which is a typewriter connected up to it. So there's no graphics, there's no nothing, so you had to do everything in text. So we'll go ahead and play a regular game. We'll go ahead and play a short game, and I'm a novice, that's for sure. Okay, then I have to type in a secret password. Now, I had to guess what this was, but the answer is pretty obvious. It's NCC 17901. All right, that is the it's the enterprise designation number. All right, so here we are. So we get a little text up there, and your printer's going mad, and we have star-based locations, and we can type in help, and it says, what do you want help on? So we type in help command. All right, so these are the valid commands we can look at. So let's look at status first. We're docked. Okay, it tells us all about the current status. And there was another one there. Now, if you mess this up, you're gonna have to print this again. So we got to do help commands. All right. Oh, these commands is like it gives you the short version. So the first thing we'll do is look at the chart. Okay, we'll do chart. So this is the overall galaxy. It's 8x8 quadrants, and we are currently in 2-3. So 2-3 is going to be, I think it's 2 over and 1 down. So we can do a long range scan, which actually shows us this shows us the quadrants around us, and then we can do a short range scan, and this shows us what's going on inside of our quadrant. So then if you go from here, then you have you can warp around the different quadrants. Then you can you have phasers, you have torpedoes, you have shields, you have shuttlecraft, you have a time limit. It just goes on and on and on. So a typical game like this might go on for an hour. Now, meanwhile, what's going on back here? This thing is printing like mad. So what you would get is a box of paper. If your printer needed some paper, there was boxes of these over there, and you'd feed one in, and you'd blow through that entire box of paper. And when it came out, it would fold back up into an empty box. And then when you're done with that side, you would take the empty box and flip the boxes around. Then you would feed that back through the other way, so you could get 2 printings on one box of paper. And you could easily go through a box of paper if you sat down there for a long time. All right, that's 77. Now, we also had... let me show you what these. Let me show you how most of this information was shown here. Let me see here. I think I can copy this one. Yeah, copy that one, and then I'm going to bring up a browser here. Oh no, that wasn't good. Hold on a minute. Got some problems here. Let me put this over here. We'll go full screen. And I think we do this over here. Here we go. So this is a magazine that had been started publishing back then. And so I'm just going to show you a few pages of this magazine so you can see. Oh wait, I gotta go back over to the stream. I kind of close that window like a fool. Here we go. All right. Okay, this is good. So this is what the magazines looked like back then. So they didn't, there wasn't, the notion of computing was in its infancy. So you'd have ads for computers, you'd have ads for kits, you'd have ads for disk drives and monitors and all sorts of things. And these were, quite expensive endeavors at that time. And most of them were sold as kits. So you'd get a kit and you'd build it. I'm going to show you this thing here, this Heath Kit H8. I'll show you that. I'll talk about that in just a minute. But you can see that it's in its infancy, and there wasn't really any kind of standards. You would get a computer based on some things you read in your creative computing, and you'd make your purchase, and you would try to get it to work. So that's the early days. Now let's go back over to. I showed you Star Trek. Now, if the next year, the high school, that DEC computer was probably donated to the high school from the lab, the Los Alamos National Lab. And its value back then was about $100,000, so it was quite a donation. But they only got deck writers for the first year, and then after that they got some more funding, and they were had replaced 10 of these with VT100s. So a VT100 looks like this. This is a terminal. This is it's a terminal with 40 characters, 40 by probably 20 lines, maybe 24 lines. And if you were a high school student and you had an account, you could get, wait, I just didn't show you. All right, so here's a deck writer. So if you're a high school student and you had an account, you could log in with a VT100. If you didn't have an account, you were relegated to only running two of the deck writers. So high school students kind of got priority. They had 9 of these terminals, and then one for the teacher, the instructor. All right, so let's the Star Trek game on here was actually a little different. Someone had modified the Star Trek game, and they were you didn't have a screen like this. It didn't scroll like the deck writer did. It actually showed you the majority of everything on one screen. And I couldn't find the source code for that. You'll just have to imagine what it looks like. All right. So what we did learn about was there were a bunch of manuals in that room. The user room. There's a bunch of manuals there, and one of the manuals was BASIC. And so one of the first languages I learned was BASIC. And let me see here. What is our next slide? All right. So what we're going to get going now is I'm going to find our window back here, if I can. If I can figure out where I left the. All right, here's our Docker instance. So we're going to. I've kind of lost my way here. All right, so we're going to install a version of BASIC in Docker. And this brings back crazy memories. And you're going to have to see what it was like to write programs for the first thing. So I have BW Basic. So you do BW Basic. And BASIC stands for Beginner's All-Purpose Symbolic Instruction Code. So this is your basic prompt shows up like this. And I think there's a help screen. Nope, there's no help. So you don't know. What do you what do you do at this point? You go and you get the manual off the shelf and you start reading. So it's an interpreter, so you actually can type in commands and run them. So the first thing you can do is like print hello world. Okay, and it would print that. So that's good. And one of the first programs that I wrote was a thing that would it printed a square on that graph paper, and it put an X in the center. So that graph paper was 132 characters wide, and I learned enough that summer to print a little program out. And I'll show you what basic looks like in case you haven't seen it. Okay, so all basic programs have line numbers, so you have to have a line number. So you're going to start out and you're going to say, and then there's this. Now I actually remembered how to do all this one. So you say let I equal 10. So I is a variable, and you come in and you say print I. All right. So then I can run this program. All right. So it printed 10. Okay. Then I can add another line. I equals I plus 1. And then we can say if I is greater than 40, then, oh wait, I forgot my line number. Shoot. 40. If I is greater than 40, then go to 100. Oh, I need a line number. 50, go to 100. And 60 was end if. That ends my if statement. And 70 is go to 20. And 100 is end. Okay. Now I know a list command works here. So here's my program that I'm going to run. So right now this is going to print from 10 up to 40, and it's going to stop. So we hit run, and there we go. So it printed 10 to 40. So that's the first language I learned how to do was BASIC. Now, it turns out that when IBM PCs came out, you could get DOS for them, and DOS also had a BASIC interpreter called GW Basic, which everyone called it GWiz Basic. And in 2020, Microsoft actually open sourced the original GWiz Basic interpreter. So, they're on the bandwagon for open sourcing stuff. All right, let's move on here. Turn that off, and we're going to shorten this window up here, and we're going to go back to our slideshow. Let me make sure I'm in. Okay, so now I'm back in. That's summer of 77. So my dad got one of these. My dad was a chemist at the lab, and he got an HP 67. And this, I believe, was one of the first programmable calculators that came from HP. And back then, that price was $450 for that. And, oh, dang it. Sorry about that. Here it is here. So this calculator was $450 in 1978, which is about $2,000 today. It had LEDs, and this was a scientific calculator that you could actually program. So the way you program it is you get the owner's manual and programming guide, and it kind of talks about your programs that you want to actually run. So this thing here was quite unique in the fact that it actually had a magnetic tape reader, a magnetic strip reader to store your programs on. So that thing would look like this. So you'd get these. Oops, sorry about that. You'd get these strips that some of them would be pre-recorded, so they would be like scientific calculations and that type of thing. But there were also blank ones. So if you had your program written, you could shove this magnetic strip through there, and it would write onto that magnetic strip, and then there was probably a place that you could write down what you had stored on there. But the first thing I was interested in is in the manual, there is a rocket landing game. Now this was back in the 70s. This is, in the middle or towards the end of the Apollo program. And what you were doing is you were trying to land this landing craft on the moon. And whoever wrote this program actually, incorporated all the physics, the mass, the gravitational force on the moon, and you would basically have a limited amount of fuel, and you had to land the rover there on the surface of the moon, and you had to be lower than some velocity when you touched down, otherwise you'd crash it. And I played that game forever. And the way you got that in the game is in the back of that manual there were key codes, and you would hit these keys and you would enter in the lunar lander into the calculator, and then you could play the moon lander game. So that was all good. And these key codes, it was kind of cryptic. Now this calculator here only had digits for the display. So a key code like number 1 here, this is number 1, the first step in my program, 312511. So this key code here equates to 3 down, 1 over, that's F. 25 is 2 down, 5 over, which is F label, and then 1 1. So that is label A. All right, so it was really cryptic to program this, but basically what the calculator would do is it would basically press the buttons for you in a very fast motion. And so you'd have to enter in all these key codes, and then you could play the game or have it do your scientific calculation or whatever. Now, that's an expensive calculator. The ones that most of the people had was this one here. It was this one, a TI-30. This was a very inexpensive TI calculator it came out with for students. And I can actually show you one that I found in a thrift store. So here's the TI-30 that I have here. And believe it or not, this one still works. Takes a 9-volt battery, and back in those days, all the displays were LEDs, and these things are really power hungry from a battery operated perspective. But you just do your calculations. Like say we wanted to do 15 times 47.9 and enter, and then here's our answer. Okay, 7185. And if you're looking at this now, you're probably seeing it's called Charlie plexing for the LEDs, where it kind of scans through and individually lights segments, and this is the way it does power saving. It doesn't keep them all on at the same time. Now our eyes' persistence of vision, oh look, it went into a screensaver mode. So you can hit any key in the screensaver mode and it takes you back. Oh nope, I messed that up. All right, so I'm going to show you a stupid junior high school trick that you can do with these things. So we're going to a lot of you who are old know what this is. 7 7 3 4 7734. Got that? Now if you turn the calculator upside down, it spells hell. So yeah, I think I got one of these when I was in 9th grade. All right, so what's our next thing over here? All right, the Heath Kit H8. So in 1980, there was actually electronics class that was taught there in high school as part of the arts department, and it was taught by a instructor named his name was Dr. Place. He was a physicist that I don't know if he couldn't get on at the lab or whatever, but he was Dr. Place, and he was off in the distance most of the time. He's in his own mind going somewhere. and we would call the classroom Dr. Place's Space. Or we could call it Dr. Space's Place. Kind of stupid. All right, let's let's go on to our next slide here. So this is a Heath Kit H8. So this, remember when I showed you the magazines? They were all kits, and so this is a kit that came out from Heath Kit, and you would get this thing and you would assemble it. It all came in kit form, so it came with circuit boards, and you would solder in all the RAM chips, the CPU at that point I think was an H8 CPU, and we spent about a year in our electronics class learning a little bit about electronics and mostly doing the assembly for our H8. So inside of here you have these RAM boards, and if you look at this, this is let me zoom in here. 16K of static RAM. So each of those boards amounted to 38K of RAM. And the way you entered in, the way you could determine what was going on was this display here would tell you information about what was in the stack, what was in the various registers inside the CPU. And if you had you could connect a keyboard to this and a television monitor, and you could actually program this after you got it booted. So there was a boot sequence where you'd power it on and you would enter in some basically some machine code, and it would start the boot process and get booted. All right, so that was in 1980. So we're going to move over here to, you can see this thing is really quite large. All right, now I was, oops, wait, I got that wrong. Did that wrong. All right, here we go. So my dad was, he had a side business, and he ended up buying an Apple II in 1980. I think it was in 1980. Yeah, I bought an Apple II in 1980, and back then the equivalent price for the Apple II was almost $1,200 in 1980 dollars, which is equivalent to $4,300 today, which is really quite expensive. Now, this is the second version that came out from Apple, and this was designed by Steve Wozniak, and there's a bunch of people that actually worked on the code for that, and this had a 6502 processor in there. And oh wait, I got a message coming from Unexpected Maker. Don't forget Boobless. I had forgot about Boobless. Yeah, all right. Yeah, so that number is going to be 5537808. Oh, we better try that one. All right, hold on a minute. Let's go back here. That's 5537808. Here you go. Boobless. Thank you, Unexpected Maker. Oh, that was classic. That was classic right there. All right, back to the Apple II. So the Apple II 6502 processor ran at a whopping 1 megahertz, and that version that we had at 48K of RAM, and it would in a high resolution mode, it had 6 colors, and that high resolution for that computer was 280 dots basically by 192, and in a low resolution mode it had 16 colors and 48 by 40 characters would come up on the screen. So the documentation for this was quite extensive, actually. So I'm going to show you what actually came with as a manual from Apple. I'll show you this here. This manual looked like this. Okay, and this manual completely outlines, only the index is in green. This outlines every aspect of the computer itself. I mean, everything. The entire hardware design, schematics, probably little schematics, how the screen worked, on and on and on. This thing here is how many pages is this? 200 pages of this thing. All right, now I think I'm going to show you some things here on the page. I read through this, and I think page 141. This page here, this is where it got interesting. So these are actually the registers. The whole thing is memory mapped. So all the I/O ports and the monitor, the screen memory, and all that stuff was mapped into memory addresses. So I had no idea how to use any of this stuff. What I did know is it also came with AppleSoft Basic. So let me show you that here. AppleSoft Basic. AppleSoft. Okay, it also came with this. Now, remember, I had gone through the Basic on that PDP-11, so I was familiar enough with how Basic worked. And in here, there actually is 2 commands that you could call from Basic called peek and poke, and that's where you could actually peek into a register inside the computer and read out the value, or you could poke a number or a value into a register, and with that I could manipulate the screen and kick it into graphics mode and put rudimentary graphics onto the screen. And this is kind of a critical thing here. So there was also some there was a reference manual. Let me go back to the other manual. There's one more thing that's kind of critical to this whole discussion. All right, so here's the RAM addresses. Somewhere in here are the commands. No, it's the ROM listing. Let me see where these are. The special. Okay, right here. All right, so these are the instruction codes. Now, you could also peek and poke assembly, not assembly, it's a machine hex code into RAM, and you could actually run with Basic. You could peek and poke the code into RAM, and then you could do basically a jump to that location, and you could execute it. And I started playing around with this, and I got to the point where I actually wrote an assembler that would take these opcodes, it's like ADC or AND or BCC. It kind of explains that up here, and how the processor works with the accumulator and the X index and the Y index and the program counter and all that stuff. I kind of figured out how to run several of these commands, and so I ended up writing an assembler that would open a text file that was on the floppy drive and read in those opcodes and translate those into the hex and poke those into the RAM addresses, and then I could do a jump. And this is the way that I was able to. I didn't even know what an assembler was at the time, but I was able to basically write machine code at that time. At that time, with just writing a little real simple assembler. Now, why this is important is, one, back then I didn't know anybody else that had an Apple computer. I didn't know that you could buy an assembler. I didn't even know what an assembler was. In fact, the notion of buying software back in those days was really was like a foreign thing. You bought a computer to learn how to use the computer, which meant that you had to learn how to do programming. The whole thing of software was, that was going to come in a big way, from in the last, about 50 years. But back then, we didn't know any better. And I also will talk a little bit about the impact of that as we go along here. All right, so that's my Apple II days. We're gonna have one more thing here. Let me close that. Oh, dang it! I went and closed the wrong window. That kind of blows. Hold on a minute. Gotta get my notes back up here. Got so many windows going, it's crazy. Okay. All right, I gotta get back over here. All right. Also, in 1980-ish or 1981, I was able to take a computer class. Because I was a high school student, I got to use the VT100 terminals, and we learned how to program in Pascal. There was C compilers back then, but C was a rather difficult thing to teach, and Pascal was a lot more friendly. So we're going to bring up our window here again, and we are going to install Pascal. So we got apt install FP, which is the free Pascal compiler. All right, so we're going to go download that. Now this is a compiler. This is a compiler, so we have to come up with a source code file. And kind of running along here. Let me show you what a Pascal program looks like. All right, so Pascal program looks like this. It has a program statement at the beginning. It tells you that we're going to call this program "Hello World," and it's got an output. And then it does its demarcation. It's basically block code identification with the word begin and end. And I think the end with a dot on the end actually signifies that this is the end of the program. So we're going to run this compiler. Except I don't remember. Oh, I think it's FPC. And we're going to do hello world.p, and it says that it compiled it. And if we look at our file here, we'll see that we have a hello world program. Actually, it's called HW, and we'll go ahead and run that. All right, so we spent we spent a better chunk of probably a year learning about Pascal and writing code and learning about functions and the structure of Pascal and all that. All right, so. So we'll go back over here, and if I can figure this out, I've dragged my window off of here. We'll go ahead and go to the. Oh, that's not the right slide. All right, hold on a minute. Where am I going here? I can't see my cursor. Okay. All right. Here's one more thing here. Okay. When I graduated from high school, it's 1981, and as a graduation gift, I got one of these. Let's see, I got one of these. This is a HP 41. And yes, I have had this in my possession. It's been on my desk for since 1981. I've kept this everywhere I go. All my companies I work for, I have this on my desk. And this is actually an alphanumeric display. So it's an LCD screen. It has these modules that plug in up here, and it's programmable as well. Well, I'm not going to tell you that story, but it's going to take a little bit too long. But this thing changed the way that I look at it. This thing changed engineering for me in such a big way. I was able to actually become a good student because I had this calculator. And I don't even know what the price was, but this was my graduation gift for when I graduated high school. And I still have it today, and it works great. Here's one little trivia for you that you probably don't know. Even after 40 years, these keys look brand new. And the reason is, when HP designed a product, this STO label here, this STO label is actually that the white characters there go all the way through the key. So no matter how worn down the face is, you will always see STO. This was at the time was the Cadillac calculator of the day, where a lot of people still had this thing, which is this is a junior high calculator. This one here is this is a real machine, and I use this all the time. And actually, I have an emulator on my phone that for when I'm out going somewhere. Okay, so back to so I went to college in down Las Cruces, and so now I've hold on a minute. I got to close the door here. All right, we'll make this pretty short. So I had a personal computer in high school, and I learned to program in BASIC, and I also learned a little bit about operating a PDP-11, which was running Unix at the time, and then I had a calculator that I could program as well. Now, when you went to New Mexico State, it was a giant step backwards in terms of the computing resources that were available for freshman students. And you probably take a Fortran class, like Introduction to Programming or something like that. And as freshmen, you weren't allowed to access like that VT100 back then. These were IBM computers, so it was some IBM monitor. But you were relegated to using one of these things. This is a IBM 29 punch card reader. So you've probably seen punch cards or even heard of punch cards, but basically here's a picture of a punch card. All right, punch card is a piece of paper, and it punches holes in the here, which is actually like it's not actually ASCII, but it's equivalent to that the machine can read in. So it reads these holes in here. And Fortran statement has 5 characters that are reserved up front, and the very first 5 can either be a label or a statement number, or they can be blank. And then you have this continuation column, whereas if you had a really long line of formula, you could put anything in the continuation column, and the next line was a continuation from that. And then up here you would have the actual printout of what the statement that you're actually executing. So back then, you'd go into a sweaty room that had about 30 of these in there, and it was pretty rank in there. And all the freshmen are out using these punch card readers, and there was no making of a mistake. If you made a mistake, you'd have to throw away that card and start over again. So you type in your commands, and you could see what was going on the screen there. And you could duplicate cards as well. And then what happened is, this was the hopper that had the fresh cards in it. And then as you typed along here on this very hard to type keyboard, this thing would march across, and the puncher for it was over here. And so it punched holes as this thing moved across. And then when it got over here, you'd say load next card, and this thing would fly out here, and it'd stack up here in the reverse order. So then you would take your stack, and you would go to a card reader and put your card deck, they called it, into a reader, and you would hit scan or some button on the reader, and the reader would scan in all your cards one at a time, and it would that would now become a job. And this mainframe that they had would run these jobs in order that they came in. And then you would basically had to sit there and wait for the printout to come out. Now what you had in there, in the room that had the card reader, had a wall that was, it probably had 60 bins in it, labeled 1 through 60. And you would put your first card deck, your first card in your card deck would say, take this printout and put it in box number 57 or whatever. And then you would run it through, and if the computer was busy, which was pretty much 24/7, you could be waiting 20 minutes for your printout to come. Now, if you had an error in your card, in your program, you would get an error statement that came out in a piece of paper, and you'd go through this thing, and you'd look, and you'd say, oh man, I had a typo in line number 77. So you'd go back over, you would find card 77, and you would retype it on the card punch machine. Then you would carefully insert that back into the slot for 67, and then you would put it back in and do it again. So the notion of writing code in this fashion was super tedious, but you got very good at finding syntax errors, because once you it could take up to 20 to 30 minutes to actually see what the output was when you ran your program. So you got very good at making sure that you did not have any mistakes, and then you had to go through and debug your actual code that you were trying to run and actually do your homework problem. So let's go on here and we'll install a Fortran compiler. This is G Fortran. Now, actually, there's a lot of people that still write in Fortran because it has a tremendous amount of libraries. All right, so we're going to go ahead and install it, and we are going to look at our Hello World program that's written in Fortran. So let's go ahead and type one in here. So did I edit? No, I didn't put an editor in here. Apt install vim. All right, let me put an editor in here so I can edit a file. All right, so we're gonna edit a file called hw.f, which is my Fortran file. So if you do like a print, and then you do a star, this star is a thing called a unit, and a star means I just want to come out on the standard output. And we're going to print out hello world, and then we have an end statement here. Okay, and we're going to save that. We're going to, I think it's fc hw.f. No, it's not fc. What is it? Didn't even write down what the command was. Oh, maybe it's G4. Okay, G4. Here we go. All right, here we go. Non-numeric character in the statement label field at 1. Oh, all right. Shows you what I know. I just finished telling you about. I just finished telling you that the first 5 characters in a line needs to be a label or a number, and then a continuation. So we got to go in and edit our file again. I'm doing this one, so we need to add 1, 2, 3, 4, 5. And that 6th one is the separation character or the continuation character. All right, so every Fortran program looks like this. So we do this again. Oh, something happened here. So what do we got here? What did it make? Let me make a new directory here called F. And we're going to move that h.f in there. All right, so I'm now working in F. I have my source code in here. So we're going to go ahead and run Fortran again. And we're going to look at our output. And we've got a.out. So a.out says hello world. Okay, so we learned how to write Fortran when I was a freshman in college. So now, by the time I was a sophomore in college, I had learned a little bit of assembly. I'd learned BASIC. I had learned Fortran, and I had learned a heck of a lot of how to play Star Trek. So, all right, let's get on to our current day stuff, because I'm going to run out of time here. All right, let's go out into this thing here. So this is called an ESP32, and it's on this little board here. And this guy here is a current production module that has a dual core CPU running at 240 megahertz. It has 512K of RAM, and also has embedded into this module Wi-Fi and Bluetooth, as well as Bluetooth Low Energy. And these boards here are available on Amazon for about $6 a piece. All right, so remember, when I first got started with computer, and I was working on I was working on basically $100,000 computer, and now we can get this thing for $7, and actually we can program a bunch of stuff on it. So what I'm going to do is I'm going to run microPython on this little board here. So the first thing I'm going to do is I need to I think we're done with our Docker instance. I think I need to, let me see here, what are my notes here? Where is the ESP stuff here? Oh, okay. So I'm going to bring up I'm going to exit out of my Docker container. And what I'm going to do is, there's a whole website. There's many websites on how to use the ESP32, as well as a bunch of tutorials and as video things on YouTube. This is a very popular development platform for product development, as well as the makers, the DIY movement here. So I think the first thing I'm going to do is I want to run this command here, which actually will flash my ESP32. Okay, so oh wait, you're not even seeing that screen. Hold on a minute. Let me start this again. All right, so sorry about that. So this is the command you run, and I've downloaded a binary version of this, which is a compiled version for microPython, and I'm using this thing that's available on the Linux side as well as Windows. ESP tool. It's written in Python, and I tell it what kind of chip I have, what my serial port is, and I want to write the flash, and I want to locate it at 1000 in the flash memory, and then here's the binary file that we're actually writing over there. So what it's doing is it's actually flashing the CPU here. So I think that CPU has about 4 megs of flash, and it's so what's going to happen is it's going to boot up microPython when this is done, and then I'm going to connect to it. And you can actually do this operation in a Docker container as well, but I didn't go through the trouble of copying the tool over to Docker, because then I'd have to install Python, and I didn't want to bother with that. But we'll get done here in just a minute. I have what do I have here? I have 4 minutes to run microPython. So, all right, when this is done, it immediately resets, and then it runs microPython on the board. But I'm going to connect to the board using a terminal emulator. And I'm going to use microcom. And I'm going to say my port is dev TTY USB 1, and the speed is 115, 200, and over here. All right, so now we have a Python prompt, and we can do things like, this has just got a small version of all the Python libraries. We can say that, and then we can say like math.py. All right, so here's pi, and I could print that out to like 20 decimal digits. So I can. These are just formatting using standard C formatting. So we can do that, and then we can do math.py. Okay, so here I have Python running, and then we can do print hello world over here. Hello walk. What do we got here? Syntax error. Oh, okay. Oh, we need to look at, let me see. I think we want to import OS. I want to say os.version. No, I don't know what it is. How do I get the Python version? Maybe it's sys. Import sys. Sys.version. There we go. So I'm running Python 3.4. So Python 3.4 requires that I have everything in parentheses. So I'm going to do hello world in parentheses, and it prints hello world. And then from here I can write standard Python code. All right, so that's what's going on. Let's finish this up here. Okay, so in my experience as a developer over this time, I struggled for almost an entire summer learning about doing Apple II assembly, and I wrote an assembler in BASIC. And this is me not even knowing what an assembler was. But that ability really sunk into me, the ability that I could figure out a lot of things, and I could determine how things work, and that is kind of been a driving force of both my academic career and my consulting career, as well as all the product development I'm doing. So I'm not too shy about figuring out how a new processor works or how a new process works, or because I was able to overcome that challenge really early on. In fact, that was the first time I actually used a personal computer. So I got to figure out a rather complicated thing that I didn't even know existed. So let's fly through to today. Let's talk about. Let me put on my curmudgeon hat. These kids these days, they don't know how good they got it. And I'll take that off, and I'm like, okay, the young developers today have several things going for them. One, their hardware is extremely inexpensive. In fact, it's almost cost-free for what I'm talking about. There's hundreds of thousands, maybe millions of open source projects for all sorts of different types of architectures, microprocessors, applications, libraries. There's just it's enormous amount of open source projects, and YouTube and blog entries are available. So if a young developer today wants to do anything, chances are they can find an example of either a video or a posting of how to do something, either what they want to do exactly or what something that's very similar to what they want to do. So all those things there, it's both a curse and a blessing, because the developers today, I don't know if they have the opportunity to struggle through what I did for the assembler. I don't know if they're going to have that. They're going to struggle with software, but they're going to have a lot of videos. In fact, they're going to have so many videos, they're not going to know which one to choose from. So what I've done for probably my first startup was right after I got my PhD. Is I started mentoring young engineers or students themselves, and I know that a lot of things they want to try to do is really quite simple to do, but I don't want to tell them how to do things. I have to specifically structure my advice or my mentorship to allow them an opportunity to go through the same type of struggle and figure out how things work. Now, another thing that's kind of a drawback to this is when I wrote that assembler for the Apple II, I was working down at the bare bones hardware. So I understood how the CPU registers worked, how you do adds, multiplies, jumps, branches, all that stuff down at the assembly level. So I can see how code that you run all works all its way down through all the layers today to get to the point where it's actually loading in these registers into the CPU and it's actually doing calculations in the CPU. Developers today will probably never get down to that level unless they're going to be a specific software developer that writes an assembly, which I haven't done that in probably 15 years. There's a lot of layers for these young developers to actually get something to work right, and so there's layer upon layer upon layer upon layer, and then that can get up to their application code. So this is like I said, it's a curse as well as a blessing. That a lot of stuff has already been figured out, and they can concentrate on the applications. So their challenges are definitely not the same as my challenges I had. And it works out that I look back at my life, and I was actually in high school, junior high and high school at the exact right time to actually live a life and watch computers evolve from being a kit that you buy out of a magazine for hundreds of dollars and you have to build, all the way up to today where we can buy a hardware platform on Amazon for $7. All right, well, if you made it this far, Thanks for watching, and we'll catch you next time on Tech Talk for Grandpa. Tech Talk for Grandpa. We'll catch you next time on Tech Talk with Grandpa. All right. Have a good evening.